Hello, my name is Angel Anikalista, metric number 107831, and today our group 6 will be presenting about heat pump.
Hi, my name is Matilda Anisandanarga. My matrix numbers is 108190. So I will present introductions. First, heat pump transfer heat from low temperature source to high temperature source using external work input. Second, more energy efficient than conventional heating system because it moves heat rather than generate it. So the system consists of four main components: a compressor, evaporator, condenser, and expansion valve. So for the project objective is develop a MATLAB-based heat pump performance simulator and to calculate coefficients of performance, heat output, and heat input.
Next, I'll describe the system which consists of an evaporator, compressor, condenser, and expansion valve. Working fluid at low pressure is heated and vaporized by heat that is supplied at the evaporator, and it results in leaving the evaporator as saturated vapor, as seen in state 1. It is then compressed by the compressor to be high pressure and high temperature, as seen at state 2. The fluid is then condensed in the condenser by releasing the heat to a heat sink which cools and turns the working fluid into saturated liquid at state 3. Then the saturated liquid that leaves the condenser enters expansion valve where its pressure is lowered and drops its temperature before entering the evaporator and starting a new cycle. Next, the methodology, which is first modeling approach. This system model consists of four distinct processes, which is isentropic compression, constant pressure heat rejection, isentropic expansion, and constant pressure heat addition. The software models a steady flow, closed-loop heat pump, which operates under ideal reversible condition. Cycle act as an efficient heat multiplier, which accepts external mechanical power to compress and elevate low-grade heat to a higher thermal potential. It also calculates the coefficient of performance, COP, heat absorbed and heat release based on condenser and evaporator temperature and compression work inputs. Secondly, the governing equations. The thermodynamic behavior of the system is governed by the following ideal Carnot relations. First, the coefficient of performance, COP, is determined from T condenser over T condenser minus T evaporator. Secondly, the heat capacity released at condenser is determined by QH equals to COP times the compression work. And thirdly, the heat capacity absorbed in the evaporator is determined by QL equals to QH minus W. There are several assumptions made for this system. The first one, negligible changes in kinetic energy and potential energy. Secondly, system operates under steady state and steady flow conditions. And the last one is it is a reversible process. Lastly, the simulation workflow. The simulation begins with user-defined input parameters through interactive graphical user interface GUI, which is developed using the MATLAB application. These input parameters include the condenser temperature, evaporator temperature, and also compressor work. With the provided inputs, the program calculates the COP, the QH, and also the QL. After the completion of the calculation, the program generates a graph of COP versus condenser temperature. Next, I explain the coding implementation. This program was designed with GUI using the MATLAB UI control elements, and the main window is created using figure elements. The GUI window we created size at 100 times 400 pixel with the title Heat Pump Performance. Three input fields are also created using the UI control edit style, where user can input such parameters such as condenser temperature, evaporator temperature, and also compressor work. Output labels are also created using UI control text style, which display the COP, QH, QL, and performance status. Calculate button is created using the UI control push button style, and graph X area are created using the access element. The calculate button triggers the compute integral function, and the string to double converts input string into numbers. Validation checks the numeric value and ensures that T condenser is greater than T evaporator. If it fails, error message pops up and stops execution. For calculation, the temperature is converted from degrees Celsius to Kelvin, and performance is classified into excellent, good, and poor. For loop generates COP values for higher TC, and a downward sloping graph is plotted with title, labels, and grids.
Next is graphic visualizations. Figure 4 show relationship between COP and condenser temperature. COP decreases when condenser temperature increases. Heat pump less efficient because more compressor work is required to maintain the heat transfer process. So the graph helps user easily visualize how operating conditions affect the overall performance of the heat pump system.
Hello, my name is Janice Dirmanchi and I will be presenting the graphical user interface GUI and simulator operation of our heat pump performance simulator. GUI was developed to provide a simple and interactive platform for user to analyze heat pump performance instead of manually performing calculations. User only need to enter the required operating parameters and the simulator will automatically calculate and display the result. The GUI is divided into four main sections, which is the input panel, calculate, button, output panel, and graph visualization. Starting with the input panel, users are required to enter three important parameters, which are the condenser and evaporator temperature in Celsius, and compressor work in kilowatt. This value defines the operating conditions of the heat pump system. Once the value have been entered, the user clicks the calculate button. This button activates the MATLAB program to perform all necessary thermodynamic calculation. The calculated results are then displayed in the output panel below. Four key outputs are shown. The first one is the coefficient of performance, which is COP, which indicates the efficiency of the heat pump. The second one is heat delivered, representing the amount of heat released by the condenser. The third is the heat absorbed, which represents the heat extracted, and the evaporator. And finally, the simulator provides a performance status that gives a quick indication of the system overall performance. In addition to the numerical outputs, the GUI also generates a graph. This graph shows the relationship between the COP and the condenser temperature. By observing the trend of the graph, users can easily understand how changes in operating conditions affects the efficiency of the heat pump system. The right side of the slide shows that the GUI window of the pump performance. For the instruction used, first, run the MATLAB code and launch the GUI. Second, enter the desired value in the input panels. Third, click the calculated button. Fourth, result will appear in the output panels and graph panels.
Next result. For these simulations, the condenser temperature was set to 25 degrees Celsius, the evaporator temperature to 5 degrees Celsius, and the compressor work to 2 kilowatt. The simulator calculated a COP 14.91, a heat output 29.82 kilowatt, and a heat input is 27.82 kilowatt. Overall performance rating is excellent. Based on the graph, high COP indicate efficient heat pump system. Small temperature difference between evaporator and condenser improve the performance. Heat pump deliver more heat energy than the electrical energy consumed. So, for comparison between figure 6 and figure 7, both graphs show that COP decreases as condenser temperature increases. Higher condenser temperatures increase compressor workload. Increase energy consumptions, reduce system efficiency. So for this part, we run the MATLAB program and enter the input value. The program then generates graph showing the heat delivers and COP of the heat pump of the system.
In conclusion, this project successfully developed a MATLAB-based heat pump performance simulator that calculates COP, heat delivered, and heat absorbed under various operating conditions. The result shows that the COP decreases as the condenser temperature increases, which agree with established thermodynamic theory. The GUI and graphical visualization make the simulator easy to use and effective for analyzing heat pump performance. Overall, this project successfully combined engineering principles with programming techniques to create a useful educational and analytical tool. That's all from our group. Thank you.